Hi everyone, welcome back. In this video, we are going to cover two types of reset design techniques, which are synchronous reset and asynchronous reset. So throughout this video, we will be covering implementation of both types of reset design techniques and the advantage and disadvantage of both type of techniques. And finally, we will see which is the best reset design technique for our design. So let's get started. So first, we are going to cover the synchronous reset mechanism. So as by the name you can see, in synchronous reset, the state of the flip-flop can only change on the active edge of the clock signal. Or in other way, if we say the reset signal can only affect the state of the flip-flop only at the active edge of the clock signal. Now, how will we implement this in Verilog HDL? So in the Verilog HDL, the synchronous reset flip-flop design code looks like this. Always at positive edge clock, if the reset is asserted, we will reset the flip-flop. Flip-flop output will go to 0. Else, if there is no reset assertion, the flip-flop output will get the input data. So now, depending on the types of flip-flops available in our standard cell library, we can have, or this code, this Verilog HDL code can realized in two types of logic circuits. So the first is, this is the first type of implementation and this is the second type of implementation. So now, depending on the flip-flop, so if you see in the first circuit, the flip-flop doesn't have a synchronous reset pin. But in second implementation, if you see, this flip-flop actually comes with a synchronous reset flip-flop. So if our flip-flop doesn't have a synchronous reset pin, then this Verilog HDL code will get realized into logic circuit something like this. So a mux will be added at the input data path, and based on the reset, if the reset is asserted, when the reset is 0, the D will be 0, else the D pin will get basically the input data. So this circuit realization will happen if we do not have a synchronous reset flip-flop in our standard set library, or if we are not going to use that flip-flop and we are going to use a simple flip-flop in our design, then this implementation will take place. Otherwise, if the synchronous reset flip-flop is present in our standard cell library and if you want to make use of that, then this logic, this Verilog HDL code basically will get realized into the circuit something like this. So hope this synchronous reset is clear. Now let's see what are the advantage of synchronous reset. So synchronous reset ensures that reset can occur at an active clock edge, and hence small reset glitches can be eliminated. Suppose you have a reset signal which is something like this, and this is scenario 1, and in another scenario the reset is something like this. So actually this is the reset signal, or this is the reset plus expected reset pulse. So this pulse is long enough, and basically if our clock signals look like this, at active edge of the clock the reset pulse will be get detected and our design will basically get reset. But if we have our reset pulse something like this, which is not a real reset pulse but a kind of glitch, if there is a glitch in our reset pulse, a small glitch, then with synchronous reset technique this pulse can be eliminated, because this pulse is a small, the width of the pulse is very small, and this will basically won't detected by the design. So our design will unwantedly not reset. So this is an advantage of synchronous reset. So similarly, for examples, if we have an external reset and the point one, the advantage one is based on the external reset. If the external reset is glitchy or there are noises on the external reset pulse, then the synchronous reset will basically make sure that any kind of glitches or noise will not affect the design. Similarly, if we do not have an external reset and the reset signal for our other flip-flop design flip-flop is generated internally, then also using the synchronous reset we can make sure that any kind of glitches which are generated by the combinational logic, because if suppose this is our reset signal, internally reset signal generated, and we have something like this A and B, and basically the AND gate output is reset signal. So because of the delay inserted here, both A and B signals are not getting asserted at the same time, and we can have a glitch at the output of the AND gate. So using a flip-flop with registering this signal with a flip-flop, which will make sure that reset will get synchronized with the clock domain, and then we do not have any kind of pulses here, any kind of glitch kind of things, and then this reset signal can go to our all the design real flip-flops. So using synchronous reset is advantageous in reset signals which are generated internally and which can have a kind of glitches introduced due to combinational logic. So this is the second advantage of reset, synchronous reset. Also, the synchronous reset generally makes sure that our design is 100% synchronous, and if our design is 100% synchronous, then there are very less chances of metastability. The further advantage is in cycle-based simulation, when everything is evaluated based on clock cycles, and or everything is basically updated or processed at every clock cycles, it is easy to work with synchronous reset because we can update each and everything based on clock cycles. So always in cycle-based simulation, it is easy to work with synchronous resets. The next advantage is by using synchronous resets and a number of clocks as a part of the reset process. So this advantage is basically comes with the a reset tree. So if we have a reset tree designed, and if the reset tree delay is too much, then we can insert the synchronous, we can insert the flip-flops actually, because the reset is already synchronous, and then to meet the timing of our reset tree, if our timing is if it is getting difficult to basically close the timing of the reset tree, we can basically pipeline it and we can introduce some flip-flops which will make sure that the timing can be closed within a clock period. So this is the another advantage of synchronous reset. Now let's see some of the great disadvantage of synchronous reset. Now the first disadvantage is the synchronous reset basically requires a clock signal to reset the design. So if our clock signal is not available, and before that if we want to make our design into a known state, so just remember that the application of reset is to put our design into a known state, right? So if the expectation is to put the design into known state even before the clock is available, then it is difficult to do that with synchronous reset, or basically we cannot do that. So the disadvantage of a synchronous reset is it always requires a clock signal to reset the design. The another disadvantage is design should ensure that a reset pulse width would be wide enough to ensure reset is present during an active edge of the clock. So if this is our reset pulse, which is basically coming inside this, so the clock period is, this is the clock period, this is the first rising edge, this is the second rising edge, and the reset pulse is basically this much. So this reset pulse will not get detected even at this clock edge as well as this clock edge. So we have to make sure that this reset pulse is wide enough so that it can be detected by any of the active clock edge, and then the reset signal can go further into our design and reset all the required flip-flops. So here we in synchronous design, we have to make sure that the reset pulse is wide enough to be detected. So this is again the disadvantage of synchronous reset. Now the third one is synchronous reset can add extra logic in the data path, and which can make the data path timing issue. For example, here we saw that with synchronous reset, this one extra mux got introduced here. If our standard cell library do not have a synchronous reset flip-flop, then the implementation of synchronous reset flip-flop will look like this, and here the extra mux is basically added in the data path. Extra mux as well as this signal, reset signal, is added in our data path. So this will add extra data path delay, and it can have effect on our timing requirements. It can make the timing requirements to meet harder. So this is the further disadvantage of synchronous reset. Now let's see the asynchronous reset design technique. So in asynchronous reset, as you see by the name itself, we do not need the active clock edge to reset the design. Our design will get reset as soon as it receives a active reset signal. So how we can implement the asynchronous reset flip-flop in Verilog SDL. So this is how we can implement the asynchronous reset flip-flop using Verilog SDL. So here if you see, either at positive edge clock or negative edge reset. So this code which is sitting inside the always block can execute either at positive edge clock or negative edge reset, unlike synchronous reset where the internal code which is sitting inside the process block can only execute at every positive edge of the clock. So here as soon as there is a negative edge reset, the flip-flop will get basically reset. So now, how this basically this Verilog STL code will get realized into the circuit. This is how it will get realized. This here is a flip-flop with asynchronous reset, and here we can see that the reset signal basically will get connected to the asynchronous reset pin of the flip-flop. Now let's see what are the advantage of asynchronous reset. So first advantage is, since synchronous reset need a clock signal to reset the design, asynchronous reset do not need that. It can be reset with or without a clock signal. Second is no extra logic added in the data path. So here we see we have asynchronous reset and there are no extra logic added. So asynchronous reset flip-flops are like basically mostly available in any of the standard cell library. So here if you see, no extra logic added in the data path, so it avoids any kind of data path timing issues. So no reset signal added in the data path logic, and reset is free from clock signal and hence will get applied always, unlike synchronous reset which will get applied only on positive edge clock. Now let's see what are some disadvantage of asynchronous reset. So asynchronous resets are basically asynchronous both at reset assertion and reset de-assertion. So the assertions can happen at any time and de-assertion can also happen at any time, unlike synchronous reset where assertion and de-assertion can happen at only active clock edge. So if the asynchronous reset is released at or near the active edge of the flip-flop clock signal. So here if you see in this waveforms, we have an active reset signal. So active reset signal basically will get applied here and it is basically released at this point. So if you see here, the release is happening. This is the rising edge of the clock, and as we saw in the timing equations when we discussed about the setup and hold time of a flip-flop, similar concept is here with asynchronous timing paths as well, where the reset signal should be stable before and after the clock edge for some time. So if this reset de-assertions happens here in this window, the flip-flop can go into metastable, because during this the flip-flop control is basically to the clock signal, and when the reset signal is basically changing at this window, then the flip-flop will basically get confused what should be propagated to the output. Either the reset signal, which is basically, if it is 0 reset signal, the reset signal 0, or the input data signal. So that is the reasons here we cannot determine what will be the flip-flop output if the reset is basically changing in this window. So in there, actually in normal flip-flops with data timing paths, we called it as setup and hold. Here also for now, let's consider it setup and hold only, but these windows are basically have a different name with asynchronous signals, and this is basically called recovery time, and this is called removal time, but they are similar to what is setup and hold. So this is a big requirement with asynchronous reset de-assertion. With assertion, this is not a requirement, because if you see, the assertion of the reset signal has to be for a quite some time, and if any flip-flops get in metastable, that also get stable, because the reset will keep applied for some time, and finally the flip-flop will come to a normal state, and which is nothing but the reset state. But during the reset de-assertion, if the de-assertion happens near the active clock edge, in that particular conditions, the flip-flop can go into the metastable state, and our design state can be lost. The second disadvantage of asynchronous reset is the asynchronous reset is prone to noise or glitches. So unlike synchronous reset, when there are glitches or noise, they can be eliminated by using the synchronous reset, because in synchronous reset, the reset pulse is detected only at the active clock edge. But here the reset is asynchronous, and it can be applied at any time to the design. So any kind of noise or glitch pulse can also reset the design, which is basically not expected. Also, asynchronous reset designs makes it difficult for cycle-based simulation. Now, one thing to remember here is the signal assertion. As I said, signal assertion is not the problem on the actual connected flip-flops. Even if the flip-flops moves to a meta-stable state, the flip-flop remains unstable only for a short period of times after assertion. After reset asserts long enough, all registers eventually settle to a reset state, because the reset is going to be applied for quite some time, and finally all the flip-flops which eventually settle to the reset state. So reset assertion, asynchronous reset assertion, is never a problem. The problem only lies with asynchronous reset de-assertion. Now let's see which is the best reset design approach. So we saw here the advantage and the disadvantage of both types of reset design techniques, synchronous reset and asynchronous reset. So in asynchronous reset, in synchronous reset, actually the problem is it always needs a active clock edge, and for most of the design that is not a requirement, because most of the designs wants to be in a known state even before the clock is running. Basically, after every design, after power off, it wants on a stable state, in a known state. So always the reset is expected as asynchronous reset, which will get applied to all of the design flip-flops, and the design basically will get to a known state. So the asynchronous reset assertion is always preferred. Then the problem with asynchronous reset is during the de-assertion of the reset. During the de-assertion of the reset, the flip-flop can go into metastable state. So here we want the reset signal to be synchronized. So asynchronous reset assertion and synchronous de-assertion is what we want, because we want our design to be in known state even before the clock is available, and also we do not want any kind of metastability. So if we want our design into a known state before the clock edge, we have to use a asynchronous reset. But if we use an asynchronous reset, then there is a problem of metastability during the reset de-assertion. Now, how we can avoid that metastability problem with asynchronous reset. So if we can use this kind of reset synchronizer, this is basically called a VDD based reset synchronizer. Before our design, this is our design flip-flop, and if we add this extra 2D flip-flop reset synchronizer, then our problem of metastability with asynchronous reset de-assertions can be eliminated. So we are going to cover the functionality of this reset synchronizer in details in one of our next video, but for now I will just explain you this reset synchronizer briefly, how it is used to eliminate the reset de-assertion metastability problem. So if you see here, these two flip-flops are basically getting the external asynchronous reset, and the output of this flip-flop 2 is basically going to our design flip-flop reset signal. So here, if you see here, when the reset is asserting, this flip-flop as well as this flip-flop will get reset, and eventually then all the flip-flops in the designs will also get reset, because they are getting the reset signal as this, the output of the register 2, which will also get reset on asynchronous reset assertion. But when the reset de-assertion happens, when reset de-assertion happens, then this flip-flop is basically, the input of this flip-flop is 1, and this, or basically it is tied to VDD, and the input of the second flip-flop is tied to output of the first flip-flop, and then the output of the second flip-flop will go to the all the reset pins of the design flip-flops. So when the reset de-assertion happens, this flip-flop output will be, so let's consider two scenarios. This is our clock signal, and our reset was, so this is active low signal, so our reset was applied and it got de-asserted here. It will remain de-asserted. So here, if you see here, it got de-asserted here. So at this clock edge, our register 1 output will be nothing but 1, and our register 2 output, see, initially when the reset is asserted, this is 0 and this is also 0. So our this is flip-flop 1, and so our flip-flop second output basically will be 0 at this clock edge, and at this clock edge it will become 1. Next clock edge it will become 1. This will go to all our design flip-flops. So this is scenario first, which is perfectly fine. Now if the reset de-assertion happens in our recovery window, if the reset de-assertion happens, this is our recovery window and the de-assertion is happening here. If the reset de-assertion happens, then this flip-flop can go into metastable. But always remember, when the reset is asserted, this output is 0 and this output is also 0. So at this clock edge, when the reset de-assertion is happening just before the clock edge, our flip-flop 1 can go into metastable, but our flip-flop 2 will not go into metastable, because the input and output both are 0 for the flip-flop 2. By the next clock edge, our register 1 output will settle, because at this clock edge the register 1 output went into metastable, but before the next clock edge this metastable flip-flop will get settled, and hence we will get a clean output from register 2. So if this is also settled, then we do not have, we in the next clock edge as well, we do not have any kind of metastability for flip-flop 2. So in short, we can say that in this reset design approach, our flip-flop 2 can never go into metastable. Flip-flop 1 can go into metastable if the reset de-assertion happens near the active clock edge, but flip-flop 2 can never go into metastable, and hence our design flip-flops are always in a non-state. They can never go into the metastable state. So this kind of approach, two flip-flop reset design approach, or this is also called VDD based reset synchronizer approach, can prevent the metastability issue which can be introduced by asynchronous reset de-assertion. So if you see here, the flip-flop can go in metastable if the reset signal is the reset signal is de-asserted near active clock edge. However, the second flip-flop remains stable at 0. since the input and output are both low and preventing any output change due to input that might occur when a reset is removed. So during the reset removal, our flip-flop 1, there is a chance that it can go into metastable state if the reset de-assertion happens near the active clock edge, but our flip-flop 2 can never go into metastable state. So I hope the asynchronous and synchronous reset design techniques and which is the best one and how we can avoid the metastability while asynchronous reset de-assertion. So all these points are clear to you. If you have any doubts, please write down in the comment section. Also, if you like this video, please hit the like button and do not forget to subscribe this channel so that you won't get missed any such videos in the future. Thank you.